The Warrumbungle National Park is one of many preserved and protected locations in New South Wales, being quite special due to its unique mountain structure. The park is home to many of Australia's native flora and fauna species, accompanied by a warm, temperate climate with plenty of rainfall. The mountain range is composed of the remnants of an eroded shield volcano, estimated to have formed around 17 million years ago, through the expulsion of thick trachyte lava that escaped through volcanic vents before cooling into the rocky formations we see today, sculpted from millions of years of erosion. The first European to sight the area was John Oxley in 1818 during his second expedition throughout New South Wales. The Kamilaroi people, the traditional caretakers of the land, established its iconic name, Warrumbungles, which means crooked mountains, and in 1953 the natural heritage of the mountain range was officially recognised and preserved as Warrumbungle National Park. To explore into how abiotic factors of an environment affect the biotic, my group of 4 undertook a simplified transect of 0 to 30 metres at a northerly aspect on an inclining slope at White Gum Lookout. At and between each mark, we recorded both biotic instances such as the number of trees, shrubs, percentage cover of forbs and grasses, as well as abiotic factors such as soil colour, depth, texture, temperature, wind speed, air temperature, etc. During the practical, one trend stood out to me. As the altitude increased progressing along our transect, the depth at our tent peg sunk into the ground changed in response. At the 0 metre mark, the whole tent peg, approximately 16 centimetres long, went all the way in, and as the altitude rose, it sunk less. At the 30 metre mark, our highest point, only long grass grew in the shallower, rockier soil, and it only sunk 5 centimetres. I then hypothesised that as altitude grew, the soil depth will decrease, reducing the amount of flora growth because of the shallower soil. Due to the very small scale of our findings, the reliability of my hypothesis was questionable, but can be backed up by the fact that higher altitudes generally have shallower soil because of harsher conditions for flora growth such as wind speeds and temperature drops. Plant decomposition takes place less often, therefore limiting topsoil for plants to dig their roots deep into. On the contrary, grass was a plant that seemed to thrive plentifully among the boulders at the 30 metre mark, holding lots of water within itself, shown by how moist the soil was underneath the grass. Not many forbs were present in the shallower soil. I therefore concluded that soil depth can change with altitude, which alters the type of flora species present in the area. Due to the wet weather conditions, our plans had to change. We didn't get to undertake a 0 to 100 metre transect as a whole group, but instead completed a shorter transect in smaller groups. This was good in some ways. It meant we could repeat the experiment by having 3 separate groups taking results instead of one large one. Results could have then been compared and contrasted, increasing the accuracy of results through averages. Unfortunately, with short time intervals to complete our investigation, our results were quite skewed and rushed due to the weather conditions. In hindsight, the weather was quite unreliable for constant results, which may have affected the accuracy of our findings, thus questioning the validity of our experiment. For future research expeditions with hopes for more accurate and substantial results, taking recordings when the weather is calmer and more constant throughout the research period will be helpful in ensuring more accurate results. Longer transects, such as the 0 to 100 transect we were originally planning, or repeating the experiment many more times, will also aid in increasing the validity of the research. For me, a much larger transect up the side of a slope would be very interesting to see how soil depth changes in response to altitude and how it affects biotic life. During my visit to the Warrumbungles, I was interested in how a tree's canopy can affect the plant growth below it. So, when we had our chance to undertake our own inquiry question, I aimed to find evidence that a tree canopy does in fact affect the biodiversity of flora below it. I hypothesised that the tree canopy would have a negative effect on the biodiversity of flora, lowering the total amount of species due to the canopy blocking sunlight from reaching the plants, reducing the efficiency of photosynthesis. My experiment included a very simple list of equipment: my phone, a quadrat, and my eyes. For my method, I took the quadrat and placed it down randomly underneath trees, where the canopy above cast a shadow onto the ground. I then counted the number of species I found present inside the whole quadrat, then repeated this process 5 more times to increase validity. For a control variable, I also repeated the same process out in the open, where plant life was not affected by the tree canopy. I would then move to a completely new area and repeat the process a total of 6 times to see if there was a difference between enclosed spaces, spaces where animals cannot get into, and open spaces. After the excursion, I then put this information into a column graph. Looks a bit messy, doesn't it? In response to this, I then averaged out the 5 results I took from each tree/plane location, and it came out much nicer with an easier to read graph. From this graph, we can clearly see that the biodiversity below a tree canopy is constantly lower than areas where species are unaffected by a tree's canopy. It doesn't seem to change much depending if the area is enclosed or not. Thus, my hypothesis is correct. A tree canopy does affect the biodiversity of flora beneath it in a negative way. To further enhance my findings in the future, repeating the method even more could make my final results much more valid. If Warrumbungle National Park choose to further their research in this area, they could utilise more advanced technology such as a light intensity meter to show how biodiversity of flora changes through specific light levels depending on the thickness of the tree canopy. Overall, this depth study was a blast to take, and I've learned many important skills along the way. Thanks for watching.